Well, it looks like we're not going to have a moderator, so I'll do a self-moderated session. My name is Todd Helwig. I'm from the University of Texas at Austin. I serve as the Vice Chair of the Structural Stability Research Council, and this is one of the talks that actually SSRC organizes on behalf of AISC. If you like stability stuff, there's obviously a lot of other talks over in the SSRC, but what we're going to be doing here today is talking a little bit about flexural members, and the whole question is my C sub B factor correct? So we're going to look at a variety of different cases that we can end up using. I'll repeat this at the end, but the PDH code, if you're looking at it for this session, is 28874. So that's 28874. So again, we're going to kind of start talking a little bit about C sub B factors. A basic outline of what we're going to be dealing with today is we're going to start off just with some very basic background information, talking a little bit about lateral torsional buckling, and really, just basic application of C sub B concepts. We use them in design just to make sure we understand a little bit about what the C sub B factor is for and how we apply it. We'll then talk a little bit about conventional C sub B factors. So these would be factors that are generally going to be in the specification. I'm primarily going to focus on U.S. specifications, so AISC and AASHTO. But if you go north of the border to Canada, they're going to have similar C sub B equations. They may be a little bit different in form, or any other place in the world they'll have a little bit different moment gradient factors. But we'll see how we can apply some of these different things. As far as the conventional C sub B expressions, we're going to look at what we do on doubly symmetric shapes. We'll talk a little bit about if we have to do any changes for singly symmetric sections. We're going to talk a little bit about the impact of load position and kind of try to have an understanding of what do we mean by that, because a lot of times transverse loads may be applied at a variety of different locations, top flange, mid-height, bottom flange of the system. Then what we'll be doing is finishing up a little bit here, talking about C sub B values for special cases. I call them special cases because they're not necessarily in the specification itself, but actually they're very common cases. There's a lot of questions that come up as you're designing where you may ask yourself, is the C sub B equation and the specification actually even applicable? And we'll look at a number of different cases. For example, continuous beams where you end up having compression actually on both flanges, but maybe you've got profiled sheeting on one flange, and what can you do in some of those problems? We'll look at uplift on roof beams, where you may get in steel structures where they're relatively light, you actually can get enough uplift to where you have the bottom flange go into compression. Then we'll talk about unbraced cantilevers and another common problem that sometimes we scratch our heads about, which is what do you do with beams during lifting? Usually in the building industry, the beams are relatively light, it's not that big of a deal. But if you get into the bridge area, actually those are very long girders and they're relatively heavy. There can be some questions about how do you evaluate the stability. But even in some applications, in industrial applications, you may have beam lifting beams and so on, and how do you evaluate the stability of some of those structures. Starting off just first though with some background information on basic lateral torsional buckling and really basic C sub B concepts. When we look at lateral torsional buckling, and we're just starting here with a doubly symmetric section, okay, subjected in this case to uniform moment loading. When we have those moments, we can resolve them into stresses on the cross section, right? And if we were to slice through the cross section, we would have a compressive resultant and a tensile resultant. But as a lot of us are aware, is that from a beam's perspective, because we have both compression and tension on a beam, it's always going to fail in what we call a lateral torsional, or sometimes we call it a flexural torsional mode. Generally, where we have a larger lateral movement, it's usually the compression flange that has the biggest lateral movement, and the tension flange, because tension doesn't really drive buckling, will usually have a smaller lateral movement, but it still will move a little bit laterally. Sometimes we may have boundary conditions, like in cantilevers. Actually, you find in unbraced cantilevers, the flange that actually has the biggest lateral movement is typically the tension flange. So it's a little bit different, but in most cases it's the compression flange which has the largest lateral deformation. If we look at the equations that we typically use for lateral torsional buckling, the most fundamental equation is the expression that Timoshenko derived, okay, that was really the expression for the elastic lateral torsional buckling of a beam section that has both what we call St. Venant stiffness and warping stiffness. So when we look at this, we usually call this term over here the St. Venant term. It's related to the uniform torsional stiffness of the section, Over here we have the warping term. It's related to really the warping stiffness of the cross-section. In some cases it's worthwhile to be able to distinguish between those two terms, because we'll talk later about some cases where you may scratch your head and wonder, do I even have enough warping stiffness to rely on, and what can we end up doing in some of those systems there. But this equation, as we show it, that was developed by Timoshenko, was really derived for uniform moment loading, where we have constant moment along the unbraced length. So this is the equation that for several years was in the specification. In the most recent last couple editions of the AISC specification, we've actually changed the buckling equation a little bit. Instead of M critical, it's in terms of the stress, and it's written in a form that looks a lot different actually than Timoshenko's equation. But actually, if you were to take this, the stress times the moment, or the section modulus here, the M critical that you would get here would be exactly the same as Timoshenko's equation. It looks very different, but it's exactly the same. When we look at these terms, actually, though, what's pulled outside the radical, this is actually the warping term out here. This term inside here is actually the St. Venant term. So again, later I'll talk about warping term and St. Venant term, and you have to kind of refer back to these two problems where which is St. Venant, which is warping. But both of these expressions, the way we've put it, are in terms of uniform moment. Okay? If we were to graph in the AISC specification the lateral torsional buckling strength as a function of the unbraced length, we're going to get a curve that looks like this. Okay? The elastic buckling solutions we just looked at, they would be valid out in this region, where we have unbraced lengths bigger than L sub r. If we have an unbraced length that's relatively short, we can actually get up to full plastic yielding of the cross-section and carry phi and p. Okay? That actually happens for unbraced lengths less than something we call L sub p. And if we're in between L sub r and L sub p, that's the inelastic buckling range. Because we have some residual compressive stresses, typically we assume a value of about 30% of the residual compressive. So at 70% of my is where we start getting into the inelastic range. Okay? But this curve, as we show it here, is really for uniform moment. Okay? In many situations, we don't have uniform moment. We have variable moment. Okay? So if we were to look at cases where we might have variable moment, in this first case, we have just constant moment. And that's what we said the buckling solution that Timoshenko derived is really valid for. If instead I have a case like, say, a point load at mid-span, okay, well then I'm going to get a moment diagram that looks like this. My maximum moment I show as M. Okay, so if this is a maximum moment of M, this is a moment of M, we can get a little bit of a feel for the fact that, well, that's going to be more beneficial than uniform moment. We're going to get a higher buckling capacity typically for this case compared to the uniform moment situation. Or if I have a uniformly distributed load, again, a maximum moment at one location is a benefit. Okay? So these cases where we have a moment gradient, typically the way we account for those is with a C sub B factor. Right? We take essentially that C sub B factor, which we're going to be looking at here, and this is the basic curve for uniform moment. For a case of moment gradient, all we do is amplify this entire curve. Okay? But we have to come in and cut off the capacity at phi and p. Okay? Now the expressions we have for C sub B, they've changed a little bit throughout the years. Right? If we were to kind of go back, we would actually see some difference. But I just want to look a little bit at what do we do with the C sub B factor in design. Okay? So we have a physical feel about what we're doing. We have this case with moment gradient, okay, where we've got a point load applied at the middle. I'm showing the unbraced length as the full span of this section here. So there's no intermediate bracing here. And then we've got that case where we had the uniform moment loading type case. Well, for these cases, we can go and get our moment diagrams. Maximum moment here would be PL over 4. Okay. Down here, we have a constant moment all along the length. And we can come in and evaluate the buckling capacity here using those previous equations with whatever our unbraced length is. So in design, what we're going to do is calculate our lateral torsional buckling capacity based upon uniform moment. Okay? And then what we would do is apply a C sub B factor to that capacity and just make sure that's greater than the maximum moment that occurs anywhere along the length of the beam. Okay? Well, that's a very basic application. I'm sure we kind of understand a lot of that. But before we move on, I want to talk a little bit about, let's say you wanted to use a computer program and try to get in and check what's my C sub B factor for a specific case of moment gradient. We can use the same basic understanding of how we apply the C sub B and just work backwards. Okay? So for example, say I had this problem right here and I wanted to evaluate it using a computer program. I could go in and create a model with my corresponding case of moment gradient, whatever loading that gives us. Normally I'd do an eigenvalue buckling analysis on that and see what's my critical load. So it's going to give me some maximum moment when this thing would actually buckle. I could do a companion analysis using uniform moment type loading, and it's going to give me a critical load under uniform moment. Well, if we just back up our understanding of the C sub B factors, then we would just look at the comparison of this M critical for moment gradient, the maximum moment that occurs along the length of the beam when it buckles under the moment gradient case, and divide it by what we had for M critical under uniform moment. And that's going to give us a C sub B factor. And that's how we do things when we're studying parametric studies to try to develop expressions for C sub B. Okay? So what we could do, this is just showing some buckled shapes out of the program BASP, but if I had that point load at mid-span, if I go through and I get my critical load here, my maximum moment at buckling would be 791 inch kips. If we look at the case under uniform moment, it's 585. And if we back that out, looking at the ratio of 791 over 585, we get a C sub B factor of 1.35. A lot of times we treat C sub B factors, though, like they're theoretical. Like every single case of moment gradient, that's exactly the C sub B factor we'd get. I actually did this analysis last night, and I got lucky. If you know published solutions, this is what we have a lot of times for published solutions for 1.35. In reality, if I had a different, say, warping stiffness on the section, I may find that a lot of times my C sub B may actually vary from about 1 1/4 up to 1.4. There's actually variations in what you end up getting for it. But you can actually do some parametric computer analysis to kind of see and study some of this to back out C sub B factors. Later, I'm going to be showing some results from FEA solutions, and this is all we've done, is we've kind of gone in and studied the behavior and backed out a C sub B factor for this. Okay, so that's just a little background. So now if we start getting in a little bit into conventional C sub B applications, both historic as well as current specification equations. Okay? If you've been around for a while, chances are you've seen this C sub B factor from AISC. This was the equation that used to be in all the specifications that we did for moment gradient. We'd have the C sub B factor 1.75 plus 1.05 M1 over to M2 plus 0.3 M1 over 2 M2, and there was an upper limit of 2.3 on here. Okay? M2 is the larger moment at the end of the unbraced length. M1 is the moment at the other end of the unbraced length. And what we had to do is here get in and look at this ratio of M1 over M2. If it was reverse curvature bending, that's a help. We take the ratio as positive. If it was single curvature, that's a worse condition. We take the ratio as negative. Now, one of the drawbacks to this equation is it's really only valid for straight line moment diagrams between the brace points. Okay? That means if your beam weighs anything, which it does, technically this C sub B equation isn't really valid. Okay? But if you were dominated by lateral load on a frame where you primarily had kind of a straight line moment diagram, it actually would work. But it was kind of a drawback that it was limited in its applicability. If you're familiar with AASHTO, AASHTO still has a form of this equation in it. Okay? They put it in terms of stress in the main body of AASHTO. If you go back to the appendix, it's in terms of moment. Now, if you read through on AASHTO, okay, and by the way, I teach stuff on steel bridge, but every 3 or 4 months I've got to go back and do some stuff on C sub B factor. It takes me about a half hour to try to remember how you use the C sub B expression. Because when you go through this one, you'll notice F2 is the largest compressive bending stress at one end of the unbraced length, taken as 0 if the stress is 0 or tensile at both ends. F0, which we're getting into trouble right now because there's not an F0 even in this equation. But we've got an F0 compressive bending stress at the opposite end of an unbraced length, negative if tension. There's a middle stress here, and these two values here are going to dictate what we actually use for F1 up in this expression. Okay? And it starts to talk about, gee, if it's concave between the brace points, I always have to sit down and say, what does it mean to be concave or convex? And it's kind of one of these things you scratch your head a little bit. And it's got some other limitations. You take C sub B equal to 1 for unbraced cantilevers. Anytime your maximum stress occurs away from the end of the section, which it does frequently, it just kind of goes through and it's got all of these different limitations. In other words, I never really, like the C sub B. So if you're in AASHTO, I would actually use the next equation we're going to look at, which is currently in AISC. If you actually read through the commentary in AASHTO, they quite frequently refer to the more robust and accurate C sub B equation in AISC, which you say, well, then use that C sub B in the specification. But AASHTO still uses this specification, or this equation. Okay? What we've had in AISC since about the mid-1990s is this equation that we show here. And what you do is you work from brace point to brace point. So you have to actually define where you have bracing on the structure and then divide that unbraced length into quarters. Okay? Whatever you have at the quarter points, M1 and M3, you put in here at the bottom in the denominator. M max is the maximum moment that occurs anywhere along the length of the section. Okay? M2 is the value at the center line of the unbraced length. One of the neat things about this equation is there's no sign convention associated with it. Okay? So I may have a moment diagram that looks like this, and normally I would say, well, gee, this is negative moment, this is positive moment. For the purposes of evaluating C sub B, I neglect all signs. So I come in here and I say, okay, my maximum moment along the length here is 100. The value at the quarter points of the unbraced length are 25 and 30. I can plug those in there. 75 at the center line. This gives me a C sub B of 1.75. Okay? This C sub B equation is valid for any shaped moment diagram between two consecutive brace points. Okay? So it actually works very, very well. If we were to compare it with the first 1.75 equation, so we're just graphing the C sub B versus various ratios of the smaller moment to the larger moment at the ends. And by the way, this is only for straight line moment diagrams. We're showing this comparison because, again, the old 1.75 equation is only for straight line. But you end up seeing that the current AISC equation as well as the older equation actually agree pretty well with one another. This light blue line here, that's just the C sub B backed out from a finite element solution, like we were talking about earlier. So you can see that the equations actually do a nice job of predicting the C sub B factor for these cases. But again, the old equation was only really for straight line moment diagrams. The current equation that's in AISC, you can have any shaped moment diagram. So if we were to compare these with some published solutions, for uniform moment, if you're to plug the same moment in for all these terms, you get the ratio 12.5 over 12.5, and what we would expect, you would get C sub B of 1. That's what you need to get for a uniform moment. For a point load at midspan with no intermediate bracing, the published C sub B value is 1.35. This equation gives 1.32. If I have a uniformly distributed load, published values of 1.12, this equation gives about 1.14. Okay? It actually works very well. In most situations, it gives you very reasonable estimates of the C sub B factor. It's conservative for most cases. Okay? There's one case that we found where it's not conservative. Okay? And that's the case if I have a fixed beam, I've got bracing at the two ends of the section, and I have a point load at midspan. Okay? It's actually, that's a very uncommon case. It's really hard to not have this load point be a brace point. So even that one case where it's a little unconservative, it actually still does a pretty nice job. So it's actually a pretty good design expression for a variety of different conditions. Okay? Now, I showed you how to go through and back out a C sub B out of a finite element analysis. One thing I didn't talk about when I was actually showing that C sub B, though, is if you actually want to go in and actually compare C sub B values with a specification equation, what you're going to find is you need to put the loading at mid-height of the section. The C sub B factors assume you have mid-height loading. In a lot of situations, our loads are not at mid-height. They're up at the top flange, or we're hanging off the bottom of the flange. Where the load is on the cross-section has a significant impact on the buckling behavior. So if we compare like centroidal loading on this section, mid-height loading, the C sub B factors that are published would be directly applicable. However, if instead I have, say, top flange loading, so the load is applied up at the top flange, which would be a common case in a lot of situations, you can kind of get a little bit of a feel. These are showing what would happen if the girders buckle and they start to twist. And if that happens, you can end up seeing here that the load at the top flange of the section tends to want to twist that beam more. Okay? As a result, you're going to have a lower buckling capacity in this case compared to mid-height loading, which means the C sub B factor for this would have a significant reduction potentially. If instead I have, say, bottom flange loading, the load's hanging off the bottom flange of the section, then what we're going to end up finding out is that as that section wants to twist, the load tries to straighten it out. As a result, you're going to get a little bit higher capacity than what you would normally predict from mid-height loading. Now we're going to look a little bit at some ways that we can modify the C sub B factor to account for load position, but the specifications don't actually say much about it, okay? And I'm going to tell you that if you have the right conditions, load position can be very substantial. Top flange loading is what you worry about the most because it's unconservative to neglect. However, we're going to talk later about some mitigating factors that make it so it's not that big a deal. But we'll talk first of all about some solutions we can use to account for load position. Just getting a feel for this, this just shows, again, some computer solutions. If I were to take and do a finite element analysis and I put the load at the top flange, this is the same basic problem we had before, but now I've moved the load from mid-height up to the top flange. In that case, my moment is around 560 inch kips, whereas centroidal loading, uniform moment loading, it was 585. If I back out a C sub B factor, and here I put a little asterisk here to kind of say, well, this is actually a C sub B with load position. The ratio of what we had for moment gradient versus what we had for uniform moment is around 0.96. That's a big reduction. If you think we got 1.35 for mid-height loading, we're not talking about a 5 or 10% effect here. It can be very substantial. Okay? One way we can account for that, we've done lots of parametric studies looking at load position, and one of the things we found that actually works real well, if you go to the SSRC guide, Nethercott over in England did a lot of neat stuff, and they came up with some curve fit expressions that you could end up using to account for load position. We looked a little bit at that. Instead of his little equations, we just found if you just use this constant 1.4 and you raise it to this exponent 2y over h times your normal C sub B expression here, it actually does a very nice job of predicting the effects of load position. So what we have here is h is the depth of the beam, say the distance between flange centroids. Y is the point of load application relative to mid-height. Anything below mid-height is positive, anything above mid-height is negative. So therefore, if I have, say, top flange loading, I would say Y is equal to minus H over 2. And the solution I would get would be my modified C sub B factor would be C sub B divided by 1.4. Okay? You want to see how that works? If we take that C sub B, we had 1.35, we divide it by 1.4. In this case, actually, again, we got lucky. It's exactly the same that we get from the finite element solution. But in general, this will do pretty well. It'll usually get you within about 5% of the theoretical value you'd get out of an FEA analysis for your system. So it's an easy way to account for load position. Okay? We're going to talk a little bit more about load position later. We'll go through a quick example, but then we're going to talk a little about singly symmetric sections and come back and talk about load position again. But let's just go through a quick example of how we might account for load position or even just moment gradient in general. We have a W21 by 50 beam that we've picked out, and we're trying to check its buckling capacity compared to the factored load that we have here of 20 kips acting in this case at the top flange of our section. Okay? Our unbraced length, we're saying we don't have any bracing along the length. That's probably a tough thing. Again, usually it's hard for your load point not to be a brace point, but we're just saying it isn't here. Our unbraced length is 20 feet, which in this case is bigger than L sub R, so we're in the elastic region. Okay? So, evaluating our modified C sub B value. I'm saying this is a top flange load, so remember Y would be equal to minus H over 2. When we take 1.4 raised to the 2y over h, we get an exponent of minus 1, just like we saw our modified C sub B factor for this case would be 0.96. Again, since we are bigger than L sub R, we can just use the elastic buckling solution. So we take our modified C sub B factor, we plug in our section properties down here. It gives us a moment of 1,533 inch kips, which if we convert it to kip feet is 128. Okay. Solving for our maximum capacity at midspan would be PL over 4 would be equal to this moment, or P would be 4 over L times that moment. Comes out to be about 26 kips, which is bigger than our applied load, so we would be stable in this case. Okay? So we could account for load position in that way. Okay? Now, as I said, I want to talk a little bit about singly symmetric sections, and we'll talk a little bit more about load position before we make some conclusions on when do we have to worry about top flange loading or not. When we get into singly symmetric sections, we usually have to go to more complicated expressions than what we had for doubly symmetric systems. A lot of times we may refer to a parameter that we call rho, which is usually defined as the moment of inertia of the compression flange divided by IY of the section. Just to have a little bit of a feel for what rho would represent, if I have a doubly symmetric section with equal flanges, IY of the compression flange is essentially equal to IY over 2. We get a rho value of 0.5. If instead I have, say, a T section with flange and tension. That means IYC is equal to 0, my rho value would be equal to 0. Okay? Versus a T with the flange and compression, IYC would essentially be equal to IY of the section, we get a rho of 1. So rho values bigger than 0.5 mean you have maybe an I-shaped section with your compression flange being the bigger of the two flanges. So, if you're between these two extremes, if I have a smaller compression flange than the tension flange, I get a rho less than 0.5. Okay? When we talk about C sub B factors for singly symmetric sections, the C sub B in AISC is not directly applicable. Okay? If I have single curvature bending, actually it works fine. So a singly symmetric section where I have single curvature bending between the brace points, generally the C sub B would be directly applicable. If I have reverse curvature bending, I have to actually get in and do some modifications a little bit. I've got a fixed beam I'm showing here, and maybe here's my moment diagram, and I have single curvature on the section here. Or I'm not sorry, but I have a singly symmetric shape with different size flanges. When we end up looking at this, okay, first of all, we have to put a modifier on the C sub B factor. And what we ended up finding that works very well here is taking the original C sub B equation and putting this modifier 0.5 plus 2 times rho top squared. Rho top here is just IY of the top flange divided by IY of the section. And we had to put an upper limit of 3 on there. Now, in addition to having a modified C sub B factor, even how we check lateral torsional buckling is a little bit more involved. Because if I were to come in here and say, okay, I have a brace at the support and a brace at mid-span, so here's my unbraced length. Okay? What I have to actually do is check that the maximum moment that causes compression in the top flange, call it M top, is less than C sub B times M critical top. So M critical top here is going to be the critical buckling capacity from a uniform moment solution treating the top flange as critical. Okay, so that'd be IY of the top flange, the section modulus of the top flange, and what I would have there. I also would have to check that the maximum moment that causes compression in the bottom flange, okay, is less than C sub B times M critical bottom, because, in this case, my bottom would be treated as IY of the bottom flange, and so on. Because we just can't tell from inspection here which flange is critical. Because in this case, actually, the moment at mid-span here is only half the value at the support. Although that's smaller, I have a smaller top flange there than the bottom flange. So it's hard to tell which one is actually going to control the buckling. So you have to check both flanges. If we just go through a quick numerical example of a problem just like that, say I've got a built-up section with a 6 by 1 inch top flange, 12 by 1 inch bottom flange. I could go and get my rho values for the top flange, my rho for the bottom. Plugging in the moments of inertia of the top and bottom flanges here, we get a rho at the top of 0.11. Okay, rho of the bottom then is 1 minus that value, or 0.89. Okay. C sub B then would be essentially the C sub B factor that we have from the AISC equation, and then we put that modifier on it, 0.5 plus 2 rho top squared. The AISC equation here would give us a C sub B of 2.38 with that reverse curvature bending. If we modify that to account for the fact that this is a singly symmetric section, it drops down to 1.25. Okay, it's a very substantial reduction. Okay? So what we do with that C sub B factor now is we have to check both the top and bottom flange to see which one would be critical. So using the equation from AISC, one of the nice things, by the way, about the AISC buckling equation for both doubly symmetric sections, what we have in doubly symmetric sections, is it's very similar to what we have for singly symmetric sections. So they take a very similar form. So I could go in here and I've got to get some properties based upon treating the bottom flange as critical. Okay, so compression in the bottom flange versus compression in the top flange. So I'm going to end up having some different section properties I'm going to have to plug into this equation right here. And then all I would do is come in and say, okay, if there's compression in the top flange, I use those properties treating the top flange as critical, come up with the buckling stress that I can then solve for the critical buckling moment for uniform moment type loading for the top flange. In this case, it came out to be 172 kip feet. Doing the same thing for the bottom flange, it comes out in this case to be 1,207 kip feet. Okay? Much higher buckling capacity here, right? But if we actually get in and start looking, the C sub B times M critical, the top flange, would be 1.25 times 172. In this case, we set it equal to the maximum moment that causes compression in the top flange, and it says that we can have about 2 kips per foot is what that section could carry based upon the top flange being critical. Bottom flange actually, even though it's a much bigger moment, actually has a much higher capacity. Okay? So we have to actually check both of them. But the C sub B factor, we just have to modify, again, to account for the singly symmetric shape. We had actually, I think it was in the 13th edition, this modification was actually included in section F2 of AISC. And essentially all it did was cause a whole bunch of questions. People didn't know how to apply it. And part of it was we had to make some changes, and it kind of dumbed down the equation, and it didn't work very well. So what we've done since is we essentially say in section F2 that, you know, for singly symmetric sections you should go and do more of a rational analysis. A rational analysis is going back to the commentary and reading and seeing this modification. Okay, so you can still go to the commentary and actually get that. So now, getting back to load position, we talked a little bit about, here was the equation that we saw earlier. Sometimes actually for singly symmetric shapes and so on, there was usually some definitions that weren't actually true in some of the literature. They used to reference load position relative to the shear center of the cross-section. What we actually found was that actually for singly symmetric shapes, you should use it relative to mid-height, and if you do that, it works very, very well. So the same thing that we talked about earlier, the same exact expression works for both singly symmetric and doubly symmetric shapes. So we could write our modified C sub B factor here as the current AISC equation times R, and R, if you have single curvature, it's equal to 1, because remember the equation for singly symmetric sections with single curvature actually work well. For reverse curvature, we end up putting this modifier on it, and it actually works okay. Okay? Now, I've talked a lot about load position, and load position's real. As I say, if you get in on an FEA analysis and you start looking at applying your load at the top flange or the bottom flange, you're going to find the C sub B factors can be very unconservative or conservative that you would get out of the specification. But the specifications don't really talk about load position. And there's a very good reason for that. There's a lot of mitigating factors that make it so there's no real big deal if you have top flange loading. Okay? Two of the major contributors are something that we call tipping effect, as well as the presence of intermediate bracing. Okay? For example, if your load point is a brace point, load position has no impact whatsoever on the bracing. Okay? Because a brace point doesn't twist. In order for the point of load application to impact the bracing, the buckling behavior, the girder has to be able to twist at that location. Okay? But even if you have, say, top flange load, like a uniformly distributed load, and you've got lots of intermediate braces or a couple intermediate braces, the effective load position goes way, way down. So it's just not a real big deal. So it's mainly only if you don't have any intermediate bracing where load position is a big issue. The other thing I say here is tipping effect. And a lot of that has to do that in many situations, load may get transferred to the beam through some other surface or some other member passing over the top of a beam. And in order for that beam to be able to buckle, it has to twist, in which case the point of load application moves out to the tip of the flange and you get a restoring torque on your section. Okay? And this is very substantial. Okay, tests were done in Germany on some non-composite girders where they actually broke the bond between the concrete slab and there was no intermediate bracing. They couldn't get the beams to buckle. Okay? In the laboratory, quite frequently, this shows some buckling tests, and this is a fancy apparatus we call a gravity load simulator. It simulates gravity load, that it doesn't provide any lateral restraint. It allows the load point to be able to buckle and not really impact the behavior. Usually when we do this through our loading system, we'll go out and have fixtures machined to a knife edge. We have them heat treated so they don't dull. And what we want to do here is simulate a point load where that beam can twist about that knife edge and it doesn't really impact the behavior. To give you a feel for things, on a test like this, if I get a certain buckling capacity, we did some other tests just throwing a 2x4 in there instead of the knife edge, it doubles the buckling capacity. It's very substantial. Tipping restraint can be very, very significant. Okay? So based upon that, we say, when is load height going to be a problem? For most practical problems, it's not that much of an issue. And when I say load height, the main thing we're worried about is top flange loading. Okay? When in doubt, usually if you just say, I'm going to use a C sub B of 1, you'll be fine. Okay? You can use the provisions that we outlined, the 1.4, raised to the 2y over h times the C sub B. You can use that for cases where you have no intermediate bracing and you're worried about top flange loading. It'll work very well. Okay? One thing you want to watch out for, though, is if you have loads stacked up on a beam. like masonry blocks over an opening, and that load point can actually rotate. If you think you see a significant drop in the C sub B raising the load from mid-height up to the top flange, if the centroid of this load is up here, it just plummets. So you really have to watch out, find a way to tie that back. You actually could estimate the impact by just taking this 1.4 raised to the 2y over h, where y is going to be from mid-height up to wherever the centroid of your load is, and you're going to find, wow, that's a really big reduction. Okay? Now, if we get into some special cases, but these are relatively common cases that actually happen in design. Okay? A very common case is a situation where the C sub B factors that are in the specification usually are defined to work from brace point to brace point. But it's pretty common in a lot of cases to have reverse curvature bending on a section, and you may end up having some lateral restraint on one of the flanges. For example, maybe I have a floor diaphragm or something here where I've got closely spaced joists connected to a flooring system. But I'm getting reverse curvature where over here I'm getting in the bottom flange at some location along the unbraced length, we get compression. Okay? So what can we do? Now, in the first thing I'll say, if you're not getting compression somewhere along the bottom flange here, move on because you don't have a buckling problem. Okay, the compression flange would be continuously laterally braced. Now, if instead you end up having at any location along the length you get some compression in the bottom flange, you can end up using this C sub B factor. And what we use for the unbraced length is the spacing between locations where you're stopping twist. Okay? So up here I've got maybe a diaphragm all in the length, and maybe I've got a joist, a bar joist, and I put a kicker out to that bottom flange. That stops twist. So I have to go from point where I stop twist to a point where I stop twist. And then what we do at the ends of that unbraced length where we define that, we say M0 is the end moment that gives the largest compressive stress in the bottom flange. M1 is the other end moment. It may or may not cause compression in the bottom flange. Okay? The value at the center line, we call M center line, and we just plug into this C sub B expression here. Now there's an asterisk right here that says take M1 equal to 0 in this term if it's positive. So if the moment over here isn't causing compression in the bottom flange, you take it equal to 0 in this last expression. Okay? To show you some computer solutions, the green line here is the C sub B that came out of FEA solutions. That C sub B equation here has almost exact correlation with the FEA solutions. Okay? You get this little change in slope right there in the case where you take M1 equal to 0 in that last expression. Now, one of the things you'll note here, you can get some very big C sub B factors here. But remember, you're using the full length of the section there where you're preventing twist. Okay? So if we just go through a numerical example, say we have again a W21 by 50, and I've got moments where I've got minus 100 to plus 200. Maybe this is for like lateral load on the frame where we get this distribution of moment. M0 is the maximum moment that causes compression in the bottom flange. That's going to be minus 100 here. The value at the center line is 50. Over here, M1 is plus 200. When we evaluate our C sub B, 3 minus 2/3, M1, which is plus 200, over M0, which is minus 100, plus 8/3, the value of the center line is 50. M0 is minus 100. We take M1 equal to 0 here because it's not causing compression in the bottom flange. Our C sub B in this case is like 5.5. It's a really big C sub B factor. Okay? But you look at this, I'm only got this little bitty amount of moment over here that's causing compression in that bottom flange, but I'm still going to use the full 20-foot length here as my unbraced length. So I plug in here, phi factor, C sub B, plugging in the section properties, get a huge buckling capacity here, 755 kip feet. I compare that with the maximum moment that causes compression in the bottom flange. And then I would check for my maximum moment, otherwise 200 kip feet with like phi and p of the section. That allows us to get in and account for a case that we end up having on this system here. Another common case that may come up is in the design of roof beams, where I've got a shear diaphragm, and it may be connected to very closely spaced joists that are really stopping the top flange, bracing it all along the length of the section. Now, if you're looking at gravity load, you can use the equation on the previous slide. Now, if it's wind load, though, in wind load, you can end up getting enough uplift if this is a flat roof to where it can cause that bottom flange to go into compression. Okay? If it doesn't, again, you don't have a buckling issue as far as that goes. But if you get compression along the length of the section, Then you can end up using some C sub B factors we're going to show here to evaluate your capacity. Okay? So we end up coming in here, we've got three different cases. One is both end moments. Again, we're saying end moments are locations where you're physically stopping twist by either having your joists that frame in or something actually stopping the section from twisting there. And M1 is going to be M1's at the larger moment at this end, M0 is the smaller moment, but both of these would be positive in this case, and at some location along the length you get compression in the bottom flange. Or you could have one end moment negative, the other one positive, or you may have compression all along the length of that unbraced length. And if you do this, you go in, and these are the different C sub B factors that you can plug in for each of these different cases. For example, in this first case, both end moments are positive or 0. So in this case, we've got them both positive. We've got 100 here. That's going to end up being my M1 value. 80 in this case is going to end up being M0. The value at the center line is minus 150. So C sub B would be 2 minus M0 of 80 plus 0.6 times M1. Plugging in M center line, we get a C sub B of 2.93. So we take that times M critical, again using the spacing between locations where we prevent twist, and we compare that with the maximum moment that would cause compression in that bottom flange. Okay? And for each of these we would do the same thing, it's just a little bit different C sub B equation. Okay? Now these C sub B equations, these as well as this factor right here, they're actually in the commentary to the AISC specification now. So again, I said in F2, they'll end up putting a reference that you can base your C sub B off of a rational analysis. Okay? These are a rational analysis. Okay? So you can go back to the commentary if you want and actually use some of those. Okay? Other tricky problems that can come up are buckling of unbraced cantilevers. The C sub B factor that's listed in section F2 of AISC or AASHTO, they assume that you have bracing at both ends of your length that you're checking. If I have an unbraced cantilever, I don't really have that. So what the AISC recommends is to use an unbraced length equal to the full length of the cantilever and to actually use a C sub B of 1. Okay? If you go back to Timoshenko, he actually did a lot of studies on cantilever beams, and instead he gives equations for the buckling capacity of cantilevers, and they're a function of the warping stiffness really of your section. Okay? But you can take them and back out a C sub B factor, and you find out that, like I said earlier, the C sub B's do kind of change a little bit. Lower bound values from the work from Timoshenko say if you have a point load at the tip of the cantilever, it's a value of 1.28. A uniformly distributed load would be around 2.04, a little over 2. Okay? However, one of the things we've got to be really careful of with cantilevers when we plug in with the length of the cantilever are some of the assumptions about the warping stiffness that we end up having. For example, if I have an unbraced cantilever, so this tip is unbraced right here, and I plug into the AISC or AASHTO or whatever a buckling expression with a length of L, what that's assuming is that my buckled shape of this top flange, if I kind of look along the length, looks like this, or that we have full warping restraint at the face of that column, so that there's going to be no rotation whatsoever. Okay? Now, unfortunately, what can happen is my web of that column can distort a little bit, and it doesn't have to distort a lot, and my buckling capacity can drop dramatically. If we look at just numerically, what we've done is created a finite element model here where we're kind of modeling the column section and looking at, as we change the column size, how much thicker the web gets and what it does to the system. So a column size of 0 means that we're preventing twist at the end of this section, but there's no warping restraint. So that beam would only have St. Venant stiffness. And for this W16 by 26 with a point load at the tip, the buckling capacity is about 2.1 kips here. Okay? If I put in a W8 by 24, now that web's got some stiffness, and that flange has some stiffness if it wants to rotate. Okay? Wow, that was a real big help. It increased by about 70 pounds. Okay? If we go up to a gigantic column, a W14 by 211, it does help substantially. Okay? We go from 2.18 up to 3.11, but this is a gigantic column. Okay? To get a feel for this, plugging in with the full length would actually give us a value of 3.6 kips. The reason for these differences right here is that the face of that column, it's not really providing full warping restraint to that beam. Okay? So we've got to be a little bit careful with that. So a very easy solution If we aren't sure if we're getting warping restraint, throw the warping term out. Okay, so you can say, okay, C sub b times pi over an unbraced length times the square root of EIYGJ. If I take this problem with the W16 by 26 and put the properties in here, I used a lower bound C sub b from Timoshenko again of 1.28. We get 475 inch kips. Okay, my maximum moment would be P times L, so I can actually solve for P critical here. It's about 2 kips. If I don't throw out the warping term, I would have estimated around 2.8 kips for this problem. And boy, I'd better have a pretty good sized column if that's the case. Okay? Now alternatively, you could get in and you could put continuity plates across the panel zone here, and that's going to really stiffen that up, and you're also going to have to take out your pocketbook and pay a lot of money. That's a really expensive detail. So a lot of times it's more economical just to get in and say, I'm going to conservatively neglect all the warping stiffness and I'll have a conservative estimate there. But anyway, it's an approach you can actually kind of take. This is one of the cases, though, like on this, if you look at what's in AISC for the buckling solution, you almost have to go to the Timoshenko's equation, which we include in a user note, to actually see where's the warping term, where's the St. Venant term. But it's an approach you can actually use on some neat problems. Okay? Now, girders during lifting are always things that some engineers have faced, and you have to kind of scratch your head, because during lifting, in order to evaluate the buckling capacity, you have to put in an unbraced length. So if you're going to say I have an unbraced length, you have to say, well, what's bracing the beam? The crane's just picking it up in a sling. It's kind of difficult. So back in around 2010, we did a lot of work on bridges, and we did some different field work and some laboratory tests, as well as a bunch of finite element work. Well, one of the things we wanted to try to do is look at the stability of the girders during picking, during lifting of the sections here. So there were 2 students, one named Andrew Hsu, one named Jamie Ferris. Actually, Jamie's here, I saw her running. She's an engineer at TxDOT. They did a lot of the parametric work here and came up with some really nice work on C sub b factors for some of these systems. Okay. This just shows a bridge girder as you're picking it. As we said, here's a single crane with the spreader beam. We have a couple beam clamps. And again, you kind of get into this where you kind of scratch your head. At no position along that beam can I get in and say I'm stopping twist. So we've got to actually try to come up with an approach that we can end up using to evaluate the stability there. So we did a lot of parametric studies looking at cases where we were varying the lifting locations. So we had a total length of L here, and we just said, well, the lifting point is a distance A in from the ends of our section. So in the middle here, we have a distance of 2 minus A. We ended up considering the effective length to depth ratio of the section, how wide the flange was relative to the depth of the section, how long the segment was, where the pick points were. We did both prismatic and non-prismatic sections. Okay. We had a 3D FEA and ANSYS. This just kind of shows as we're picking this up and what the girders look like when they end up buckling. Okay. This just shows as we vary the lifting points how the buckling mode changes. So if we're out near the ends of the section like we would expect, it kind of almost buckles like a simply supported section where the maximum deformations occur out near mid-span. And as we start to move the lifting points that are represented by these yellow lines in, what happens is the buckling mode changes quite dramatically to where instead of being controlled by the region in between the lifting points, it starts to get to be controlled by the overhangs. Okay? So we got in and did a lot of work. Now the first student, Andrew Hsu, was going in, and when he was doing the C sub b work, so this is just a graph of the C sub b versus A over L, where A is the overhang limit. Okay? I apologize for some of the small fonts. Last night about 1 o'clock in the morning, I thought I'd put this in, so I had to go back to a thesis and start grabbing figures, and I didn't have the original ones to change the fonts on here. But when Andrew was doing his work, one of the things he was doing was kind of looking at, is the buckling capacity dominated by the overhang, or is it dominated by the region between the lifting points? So he ended up going through and backing out a C sub b kind of from those expressions. Later, when Jamie was working on this stuff, we kind of realized, well, maybe a better approach here is to always define our unbraced length as the total length of the segment. And that way, if someone's looking at this and they want to change where their lifting points are, all it's going to shift is going to be the C sub b that we define. So these are actually representing the same exact analysis results. It's just here we're using the critical region, either the overhang or the portion between the lifting points. In this one, we're just always defining the buckling capacity using the total length of our section. So since it is the total length, we're getting gigantic C sub b's in some of these cases. So we thought this was a better approach. So that's what we've done in all of our subsequent analysis. As I said, we did prismatic sections along the length. We also did non-prismatic sections. We wanted to come up with a simple approach, though, from an engineer being able to take into account a non-prismatic section. So one of the things we looked at as far as which cross-sectional properties do we use to evaluate the buckling capacity. Okay? In blue, we said the controlling region, or the controlling moment. That means whether or not it's the portion in between the hooks or whether it's the overhang region. In red, we have, what if we use a weighted average along the length? And that's kind of a pain, because you got to go and start using some average section properties. And then we said, well, let's just use the smallest cross-section. And actually, that actually worked pretty well for a lot of the things that we end up doing. But you end up seeing here, as we vary the lifting location, you get some huge swings in the C sub B factors. Okay? So we ended up doing some cases here where we had, regions out here which had smaller flanges, and this would be representative like a negative moment region where the flanges get much larger. Okay? And this just shows some graphs for some different flange width to depth ratios, how the C sub B factors would change. These little black lines, okay, those are going to be what we're going to use to define our C sub B factor. We tried to choose something kind of towards the bottom of each of these regions. Okay? So, depending on where we pick it up, our C sub B is actually going to jump. Okay? Instead of trying to get some fancy equation, which was really difficult, we're just going to do some very simple recommendations. Okay? This shows some non-prismatic sections when we ended up having, like some unsymmetric layout of the cross section. We're smaller here, bigger over on this region. And again, here show where those C sub B's that we're going to recommend. We looked at cases where in a non-prismatic section like here, where you choose, the director is going to choose to pick it up is a lot of times going to have different overhang lengths. So we were always looking at A as defined as the average, A1 plus A2 over 2 on the section. Okay? And what we ended up recommending was that if you pick the section up with an A over L less than 0.225, which means you're out at around 20% of the length or whatever, you use a C sub B of 2. Okay? If you're between 0.225 and 0.3, a lot of times we target like around the quarter points of the section, huge C sub B, 6. But remember, you're using the total length of this segment. So like if you're doing a bridge girder, you may be lifting 180 or 200 foot long girder, so you need that very large C sub B value. And if you're greater than 0.3, there's a value of 4. There's obviously some limitations here. Like I hope someone doesn't go in and try to pick it up right at mid-span and think they're going to have a very stable system. So there are some practical limits here, but these were the different C sub B's that we had kind of recommended. Okay? So just to kind of summarize, there's a lot of different C sub B factors that you end up having for different applications. And a lot of times if you don't really trust the C sub B factor, I actually showed you, go calculate your own. You can do that now with most software. It'll do eigenvalue buckling for you. You just have to take the case of moment gradient that you have, the case of uniform moment, and that ratio of the maximum moment gradient moment to the uniform moment will give you a C sub B factor. But you should also understand, where you need to put loads and things. We talked a little bit about load position and so on. The AISC equation, it's a simple solution. It provides a pretty good estimate and pretty good reflection of the benefits of moment gradient. For singly symmetric sections, as we showed, you do have to modify it when you have reverse curvature bending. That modifier is back in the commentary to the AISC. Okay? The C sub B factors, as we said, they're primarily for mid-height loading. If you have top flange loading, we showed you some solutions that you can end up using to modify it. In most situations, if I have top flange loading and some of those mitigating factors I talked about, I still would just use the C sub B factor because, again, load position is only a real problem for cases where you have no intermediate bracing and no tipping restraint coming. We talked about cases where you had reverse curvature bending, where you may have lateral bracing on one flange but not the other flange. Those are now in the commentary to the specification, both if they're from gravity load as well as from uplift. And then for girders during lifting, we recommend using the buckling capacity that you would predict using the entire length of your section. We chose to base the properties off of the minimum section that you have along the length. And the C sub B factors we have just depend on where you pick the section up. Okay? But that's essentially all I've got in here to summarize. I'll be happy to answer any questions that I might have raised or something that you may end up having. Yeah.
Regarding the picking, if you're picking a beam, a lifting beam with multiple
Yeah, the question is, you know, in some situations, I didn't put a picture up there, but, you know, a lot of things what we end up seeing frequently is two pick points where I end up having a spreader beam, but it's not uncommon to actually go and have, you know, sometimes a spreader beam with, say, two lift points where there's almost a separate spreader below it. Sometimes you'll pick up with two cranes that each have a separate spreader. That actually gives you a lot of benefit from the standpoint that it spreads the moment out and it changes your moment diagram. We started out thinking, should we do this? But unfortunately, you start getting the case where there's like an infinite number of cases that you can check. So usually what I would kind of recommend is that those pick points are not a brace point, and the crane doesn't really provide any bracing. So what I would probably do is still use the recommendations that we show here, but when you do your analysis on that, you're going to find you have a much more beneficial maximum moment, because it'll spread that moment out. So you would do your structural analysis, right, kind of saying, I've got pick points at these different locations, get your maximum moment, and I would still use probably the C sub B factors that we have using the entire length of the section. Okay. Any other questions? Yeah.
Would you apply this to a crane beam with a cap channel, and would you consider a crane beam with a cap channel as the case where the load point is not a brace point?
A lot of it depends a little bit. So when you say a crane beam, are you talking about the rail, or are you talking about like a bridge crane or?
Bridge crane with a cap channel on a W.
Okay, but we're checking the stability of the rail though, not the bridge portion, right? So yeah, this would work fine. What I would do in that situation with the rail, the question, by the way, I need to repeat because they're recording this, is what do you do when you end up having like the rail of a crane and it's got a cap channel on it as far as evaluating the stability? First of all, the cap channel is going to make a singly symmetric section, right? So you have to look and see, is it reverse curvature or is it single curvature? If it was reverse curvature, you'd do some of the modifiers that we end up talking about for singly symmetric sections. The C sub B factors themselves, yes, would be directly applicable. In that situation, I would not necessarily count on the load point being a braced point, and I'll qualify that in a second here. I would, in that situation, typically take it as with top flange loading, because again, you're not going to get that much tipping restraint from the wheels of the bridge and so on, as far as, you know, the section can twist and it is applied at the top flange. So I probably would actually use the 1.4 modifier. Now, one of the things, though, you can do, a lot of times when you look at the wheels of the bridge crane and so on, they typically do kind of overlap the crane and stuff to give some lateral restraint to that. So a lot of times what ends up happening, if you've ever done, like, say, the summation of P concept for frames, right, where we get in and we start looking at what happens in the sway mode of a frame, okay, where we sum up the contributions of each of the members and we carry it to the sum of the load, you can actually do that in cranes. Because it's kind of the same thing, that bridge is actually joining the two rails on either side together. Because I've known engineers that when they're designing a rail, they look at the worst possible condition and they say, I'm taking the load all the way over to one side and I'm going to check this, you know, the bridge, the crane rail with the full load that the crane has to have. In reality, what you find out is because that bridge links the two beams together, one of them can't displace laterally and twist without kind of pushing the other one over as well. As a result, what you're going to end up seeing is the capacity of one of the rails plus the capacity of the other rails. You compare that with the total capacity of the crane, and actually it'll do a very nice job. Okay? Any other questions? Okay, well, thank you, and hope you have a good rest of the conference.